Welcome to the Deep Dive. We dig into the sources to pull out the key insights, just for you. Today we're looking at something really fundamental in force measurement, but maybe a bit overlooked sometimes. Signal conditioning and amplifiers for load cells. Sounds technical, maybe a detail, but we're going to see how it's absolutely critical if you need accurate data. So the problem starts here. Your load cell, it puts out this tiny electrical signal. We're talking millivolts. Often it's specified as millivolts per volt of excitation. That per volt part is pretty important, relates to sensitivity. But yeah, try using that raw signal directly. It's going to get swamped by noise or distorted. Measurements go out the window.
Exactly right. And that's precisely where signal conditioning comes into play. Its whole job, really, is to take that signal, that almost inaudible whisper you mentioned, and turn it into something clear. Robust, like making one voice stand out clearly in a really noisy room. It's not just about making it louder, though. It's about boosting the signal relative to the noise, improving that signal-to-noise ratio, and amplifying the output so it's actually useful for whatever system comes next. Plus, these days, often converting it to digital, too. So yeah, our mission here is to really get why this step isn't optional, why it's absolutely essential for getting force measurements you can trust no matter what you're doing.
I like that analogy, the whisper in the room. It really paints a picture. So is it just about making it louder? Is amplification the main challenge here? Or are there other things going on?
Well, amplification is definitely the first thing people think of, make the signal bigger. But honestly, the real trick isn't just cranking up the volume. It's doing that without also cranking up all the background static, right?
Okay, so quality over just quantity.
Exactly, and that's where active conditioning really makes a difference. It's not just gain. It's also about smart filtering.
Yeah.
That's huge for getting rid of unwanted noise.
Noise like what? Electrical interference.
Yeah, electrical interference from maybe other machines nearby, even subtle vibrations in the setup. Filtering helps kind of tune all that out, so you're left with just the force reading you actually care about.
Okay, that makes sense. Cleaning up the signal after it's made. But looking at our sources, it seems like there's also something important happening before that, right? With powering the load cell.
Oh, absolutely. That's a really critical point, often missed. It's not just about giving the load cell power, any power. A key job for these conditioners is providing a really stable excitation voltage.
Excitation voltage, that's the power to the load cell.
Precisely. Think of it as the clean, steady power source the sensor needs to do its job, converting force into that initial tiny electrical signal. If that excitation voltage fluctuates, even a tiny bit,
The system thinks the force changed.
you got it. The system mistakes those voltage wiggles for force changes. It introduces errors that are, frankly, a nightmare to track down later.
Right, like trying to measure with a ruler that keeps stretching and shrinking. And sometimes, don't the load cells themselves have slight imperfections, like a baseline offset or the gain isn't quite perfect?
Yeah, manufacturing tolerances. So another thing conditioners let you do is tweak that. You can adjust for offset, fine-tune the gain, so the output signal range is exactly what you need for your specific system. Zeroes it out, scales it correctly.
Okay, so stable power, clean signal, correct scaling. What else? You mentioned digital earlier.
Right. So with everything moving towards digital control and data logging, many modern conditioners include an ADC.
Analog to digital converter.
Yep, so that nice, clean, conditioned analog signal gets turned into digital data, makes it super easy to process, store, feed into a computer, integrate with PLCs, whatever you need.
Opens up a lot of possibilities.
Definitely. But, like any vital piece of gear, you can't just pick any signal conditioner off the shelf. Choosing the right one, that's often where the careful engineering comes in. What are the big things to watch out for?
Yeah, good question. It's definitely not one size fits all. I mean, first base, it has to be compatible with your load cell type. Seems obvious, but crucial.
Right. Wheatstone bridge, piezoelectric, whatever it is.
Exactly. And if you're measuring multiple forces, you need enough channels on the conditioner, right?
Absolutely. Got to handle all your inputs without compromise.
And then there's the input range.
Oh yeah, big one. You need to make sure the conditioner's acceptable input range can handle the full output swing of your load cell.
What happens if it doesn't?
You'll clip the signal. It's like, imagine recording music, but the microphone can't handle the loud parts. It just cuts them off flat.
So you lose the peaks or the troughs of your force measurement.
Exactly. Your data is basically incomplete, distorted, not good. It's like trying to capture a whole orchestra's sound through a tiny little speaker. You lose all the dynamics.
Okay, clipping is bad. What about filtering? You mentioned that earlier for noise.
Yeah, and it's especially critical if you're doing dynamic measurements.
Like impact tests. or things cycling really fast.
Perfect example. For those, you need filtering that can actually keep pace with those rapid changes in force, which ties directly into the bandwidth, especially if there's an ADC involved.
How so?
Well, if the ADC's bandwidth, its ability to capture fast changes, isn't high enough, your digital signal just won't accurately show what the load cell is really seeing, even if the sensor itself is fast.
So your sensor might be performing perfectly, but the conditioner can't keep up, and you wouldn't even know it from the data.
Precisely. Bottleneck. And related to that, you got to make sure the output signal type matches what your DAQ system or controller expects.
Right. Voltage, current loop, digital protocol.
Yeah.
They need to speak the same language.
You don't want to wire everything up and then find out they can't communicate.
Yeah, that would be frustrating. What about noisy environments along cables?
Good point. For those situations, sometimes inline conditioning is a good idea. Basically, putting a conditioner closer to the load cell itself before the signal travels down a long, potentially noisy cable run to your main beta system protects the signal integrity early.
Smart. And then there's the physical environment itself.
Can't forget that. If you're operating somewhere harsh, high humidity, really hot or cold, lots of vibration, maybe a factory floor.
Your conditioner needs to be tough enough.
It needs to be rated for those conditions.
Yeah.
You need ruggedized housing, maybe specific temperature specs. Using standard lab gear in an industrial setting is asking for trouble and bad data.
Okay, so pulling this all together then, what's the bottom line for someone listening?
Well, fundamentally, signal conditioning takes that raw millivolt per volt signal.
Which is the purest measurement right off the sensor.
Exactly, the most accurate representation. It takes that and transforms it into something usable, something reliable. And importantly, something compatible with whatever else is in your measurement chain.
And if you skip this step, or maybe just don't pay enough attention to getting it right,
then your measurements, well, they could be noisy, unstable, off calibration, or just fundamentally wrong. You're basically building your analysis, maybe even your whole project, on shaky foundations. You can't trust the numbers.
But when you do get it right, the impact is pretty huge, isn't it? We're enabling super precise force measurements everywhere. Think about stress testing tiny medical implants where safety is paramount.
Or running huge industrial machines efficiently, monitoring forces to prevent failures.
Or even, making sure the structure's holding a rocket together on the launch pad or sound. That's all relying on accurate force data.
It really is. So the key takeaway for you listening has to be, don't just focus on the load cell. Yes, the sensor is important, but pairing it with the right signal conditioner is just as critical. It's essential to get the performance and accuracy you actually need from the whole setup.
It's like the unsung hero behind the star performer.
That's a good way to put it. Makes the star shine.
And as we wrap up this deep dive, it makes you think, doesn't it? How many other critical behind-the-scenes components like this exist in all the technology we use every day? These bits of engineering quietly translating raw, messy data into reliable information, making incredibly complex systems just work seamlessly without us even noticing most of the time. Something to consider.